Imagine this, a gaping wound has opened on the sun. December 2025, winter solstice, its size 62 times the diameter of Earth. Scientists call it a coronal hole, but that's only the beginning of the story. Through this breach, a torrent of charged particles is racing towards Earth at a staggering 1 million miles per hour. The sky lights up with auroras in places where they've never been seen before. But that's just the start. Beneath our feet, something may be awakening. 2025 is already one of the most seismically active years we've ever recorded. And now, new research hints at a possible link between solar activity and earthquakes, something we're just beginning to unravel. Remember the Carrington Event of 1859? It crippled telegraph systems across the globe. Fast forward to today, a solar storm of that scale could wreak havoc, knocking out power grids for months, crippling satellites and costing trillions. NASA's Parker Solar Probe recently flew closer to the Sun than any man-made object ever has. Travelling at 430,000 feet through blistering temperatures of 1800 Kelvin, it uncovered secrets that are rewriting everything we thought we knew about our star. The Sun is anything but silent. It's not predictable, and right now it's targeting us. So the question remains, can we survive the fury our star might unleash? And if we don't, who will pay the price? Chapter 1, The Sun's Shadowy Breath. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. December 2025. The winter solstice wraps half the world in its longest night, a fitting backdrop for a cosmic event unfolding 93 million miles away. Our closest star, the giver of all life, appears to bear a wound. Not of flesh and blood, but a vast dark region stretching more than 62 times the diameter of Earth, visible only through the specialized eyes of telescopes attuned to ultraviolet light. To an observer unfamiliar with these spectral visions, it would seem as if a piece of our star has been torn away, a gaping void in its fiery surface. This darkness, a trans-equatorial phenomenon, slices across the Sun's face from its northern hemisphere through the equator and deep into its southern regions. Scientists call it a coronal hole, and this particular one, emerging as 2025 draws to a close, stands among the largest observed in the 21st century. Its sheer scale is humbling 500,000 miles across. Imagine our entire planet lined up 62 times. It would still not span the width of this colossal void, yet calling it a hole can be misleading. The Sun hasn't physically developed a gap. What we witness is far more intricate, far more consequential for every living being on the third rock from the Sun. It's a region of depletion, a place where the Sun's outer atmosphere, the corona, becomes sparse and dim. To truly grasp the nature of a coronal hole, one must first reconsider the Sun itself. It isn't a solid burning ball. Instead, it's a dynamic churning sphere of plasma, the fourth state of matter, where temperatures are so extreme that atoms shed their electrons, becoming a superheated gas of electrically charged particles. At its core, where temperatures reach an astonishing 27 million degrees, Fahrenheit hydrogen atoms fuse into helium, unleashing the immense energy that sustains life on Earth. But our story of coronal holes begins much further out in the outermost layer of the solar atmosphere, the corona. This region is a paradox. While the visible surface of the Sun sits at a scorching 10,000 degrees Fahrenheit, the corona inexplicably reaches temperatures of 2 to 3 million degrees. This staggering temperature gradient puzzled scientists for decades. How could the atmosphere be hundreds of times hotter than the surface below it? The answer lies in the Sun's magnetic field's invisible lines of force that weave through the star like a vast three-dimensional tapestry. These fields, in their constant dance of twisting, snapping and reconnecting, release tremendous energy, heating the surrounding plasma to extraordinary temperatures. In most areas of the corona, these magnetic field lines form closed loops, arching up from the solar surface, curving through space and plunging back down again. The superheated plasma follows these magnetic pathways, trapped within their invisible architecture, glowing brilliantly in ultraviolet light. But within a coronal hole, a different process unfolds. the magnetic field lines do not loop back. Instead, they stretch outward, extending deep into interplanetary space, like open highways with no return. The plasma normally held captive is now free to escape, flowing outward along these open magnetic channels at tremendous velocities. This is why coronal holes appear dark. They are not empty, but rather profoundly depleted. The hot glowing plasma that typically fills the corona has streamed away, forming what we know as the solar wind. What remains is cooler, less dense, and considerably dimmer than the surrounding regions, appearing as patches of shadow against the blazing face of our star through the specialised eyes of our space-based telescopes. The trans-equatorial coronal hole now dominating the December sky is particularly significant. Unlike many coronal holes that emerge near the sun's poles during quieter periods, this one cuts directly through the sun's middle, crossing the solar equator, like a dark river dividing continents. This positioning holds enormous implications for Earth. Our planet orbits the sun along the ecliptic plane roughly aligned with the solar equator. When a coronal hole opens near the poles, the high-speed solar wind it releases typically shoots off into space at angles that largely miss our world. But when a trans-equatorial hole opens and rotates to face Earth, we find ourselves staring directly down the barrel of a cosmic plasma cannon. The high-speed stream emanating from this December coronal hole travels at approximately 500 kilometers per second, exceeding 1.1 million miles per hour. At this incredible velocity, the solar wind reaches Earth in just 2 to 3 days, significantly faster than the normal, more leisurely solar wind that constantly flows past our planet. When this swift stream collides with our planetary magnetic shield, the magnetosphere, the impact triggers what we call a geomagnetic storm. As you watch this, instruments worldwide are registering these effects. Magnetometers in northern latitudes detect fluctuations in Earth's magnetic field strength. The KP index, a global measure of geomagnetic disturbance scaled from 0 to 9 climbs to 5 or higher, signalling a significant event. The aurora oval, that majestic ring of dancing lights encircling the polar regions, expands southward. People in places like Montana, Washington, and the upper Midwest who have never witnessed the northern lights suddenly spot them from their backyards. But the sheer beauty of these celestial displays can mask potential dangers. Our modern civilization thrives on interconnected systems, all exquisitely vulnerable to space weather. Satellites orbiting Earth experience increased drag as the upper atmosphere swells with energy from geomagnetic storms potentially altering their orbits. GPS signals degrade as the ionosphere becomes disturbed, affecting navigation for everything from aviation to agriculture. High-frequency radio communications vital for aircraft traversing polar routes can black out for hours, severing crucial links. Power grids, the backbone of modern life, experience voltage fluctuations. As geomagnetically induced currents, GICs flow through their long transmission lines. In 1989, a geomagnetic storm rated only as moderate by historical standards plunged Quebec into a 9-hour blackout, leaving 6 million people without electricity. The coronal holes appearing during this current solar cycle are generating conditions that could surpass anything we've encountered in the modern technological era. What makes the present situation particularly noteworthy is its timing. We are currently in solar cycle 25, the 25th 11-year cycle of solar activity, systematically observed since 1755. Every 11 years or so, the sun's magnetic poles flip, and activity builds from a quiet minimum to an explosive maximum, before declining again. Scientists initially projected solar cycle 25 to be weak, much like its underwhelming predecessor cycle 24. They were profoundly mistaken. By October 2024, the sun had reached what NASA and NOAA officially declared as solar maximum, the peak of the cycle. Sunspot counts dramatically exceeded predictions. The strongest solar flares, colossal explosions releasing energy equivalent to billions of nuclear bombs, erupted with surprising frequency. And coronal holes, which typically become more common and larger during the descending phase after solar maximum, began appearing at unusual sizes even as we were still climbing toward the peak. The December 2025 coronal hole is not an isolated event. Throughout this year, a series of gigantic coronal holes have rotated across the Sun's face, each one showering Earth with high-speed solar wind streams. Some researchers are now questioning whether we've entered a particularly active period that could persist for years, potentially, through the descent towards solar minimum around 2030. The implications of this intensified activity extend far beyond flickering lights and degraded GPS signals. Emerging research suggests profound connections between solar activity and processes deep within our own planet. Studies published in prestigious journals like Nature have found statistically significant correlations between proton density in the solar wind and the occurrence of large earthquakes worldwide. The precise mechanism remains debated, but the accumulating data is increasingly difficult to dismiss. When the Sun sends charged particles streaming toward Earth, something in the crust and mantle below our feet appears to respond. 2025 has already proved to be one of the most seismically active years on record. Is this a mere coincidence, perhaps? But the recurring timing of earthquake swarms with solar wind impacts has raised eyebrows among a growing number of researchers willing to investigate connections that mainstream science once dismissed as fringe speculation. We are learning that we inhabit not an isolated world, but one embedded within the extended dynamic, and at times, violent atmosphere of our star. The coronal hole staring at us now is a potent reminder that 93 million miles offers less protection than we might hope. The Sun sneezes, and Earth catches a cold. The Sun opens a wound in its corona, and our satellites wobble, our power grids strain, our auroras dance, and perhaps even our tectonic plates shift. In the chapters ahead, we will delve deeper into this celestial drama. We will explore the exact formation and profound significance of coronal holes, tracing the history of the 11-year solar cycle, back through centuries of human observation. We will follow the solar wind on its arduous journey from the Sun to Earth, examining the dramatic consequences of its collision with our magnetic shield. We will revisit the Carrington Event of 1859, the most powerful geomagnetic storm ever recorded, and confront the chilling question of what such an event would mean today. We will investigate the controversial yet growing body of evidence linking solar activity to earthquakes, challenging our assumptions about geological forces. We will journey alongside NASA's Parker Solar Probe as it flies closer to the Sun than any human-made object in history, rewriting our understanding of our star's immediate environment. We will stand beneath the aurora, deciphering the physics that paints the night sky in greens, reds and purples, and look toward the future, asking what our stormy star has in store for a civilization increasingly dependent on technologies vulnerable to space weather. The dark wound on our star is not closing. If anything, the pattern suggests more and larger coronal holes in the years ahead, as we descend towards solar minimum. Each one will send its invisible river of charged particles washing over our world. Most of the time, our magnetic shield will hold the disruptions minor the aurora's beautiful. But someday, perhaps soon, a coronal hole or coronal mass ejection will prove too powerful to dismiss. Understanding what is happening 93 million miles away has become essential knowledge for a technological species. The Sun gives us life. It can also remind us with humbling force that we remain small creatures on a small world, utterly subject to the whims of a star that has burned for 4.5 billion years, and will continue burning for 4.5 billion more. The wound is open. Let us learn what it truly means. Chapter 2. What is a coronal hole? Unveiling the Sun's magnetic architecture. The very name, coronal hole, seems to contain a contradiction. How can the Sun, that blazing sphere of nuclear fire, possess holes? The answer demands that we shed our terrestrial assumptions and think instead in terms of dynamic magnetic fields, intricate plasma physics, and the bizarre behaviour of matter at temperatures far beyond anything we encounter in daily life. Imagine for a moment that you possessed an enhanced sense, capable of perceiving magnetic fields, not just the narrow slice of the electromagnetic spectrum visible to our eyes. If you were to gaze upon the Sun with such vision, you would behold something truly extraordinary. Invisible lines of magnetic force erupting from the surface, curving gracefully through the corona, and then diving back down again in elegant arcs. These are closed loops trapping plasma, like invisible bottles, holding superheated gases in place, and causing them to glow brilliantly in ultraviolet and X-ray wavelengths. But in certain regions, your enhanced vision would reveal something distinctly different. Here, lines of magnetic force do not loop back. Instead, they stretch outward, reaching towards the vastness of interstellar space, never returning. These are the open field regions, and critically, the plasma here is not trapped. It flows outward along these magnetic highways at tremendous velocities, leaving behind a region that is cooler, less dense, and therefore darker than its surroundings. This precisely is what we call a coronal hole. The term itself wasn't always in use. Early astronomers studying the Sun lacked the means to directly observe these elusive features. The corona itself was invisible, except during those rare and awe-inspiring moments of total solar eclipses, when the moon perfectly obscured the blinding solar disk, revealing the pearly white atmosphere surrounding it. Some eclipse photographs from the 19th and early 20th centuries hinted at darker regions near the poles, but without the ability to observe in ultraviolet light, scientists could not fully comprehend what they were seeing. The crucial breakthrough arrived with the Skylab mission in 1973. For the very first time, astronauts and instruments orbiting above Earth's obscuring atmosphere captured soft X-ray images of the Sun with unprecedented clarity. They're unmistakably visible of vast dark regions in the corona. Today we routinely observe coronal holes using a fleet of advanced spacecraft, including NASA's Solar Dynamics Observatory SDO, the joint ESA and NASA mission SOHO, and the newer GOES satellites which continuously monitor space weather for the National Oceanic and Atmospheric Administration. These sophisticated instruments capture images at specific wavelengths, particularly around 193 and 211 angstroms, in the extreme ultraviolet range, where the contrast between the normal glowing corona and the darker coronal holes is most striking. The underlying physics explaining why coronal holes appear dark is elegant in its simplicity. The closed magnetic loops of the normal corona trap plasma at temperatures of 1 to 2 million Kelvin, and this superheated gas radiates intensely in ultraviolet wavelengths. However, in coronal holes, where the magnetic field lines open directly into interplanetary space, the plasma is liberated free to escape. What remains is considerably cooler, typically 700,000 to 1 million Kelvin. While still unimaginably hot by terrestrial standards, it is cool enough and sparse enough to appear dark in contrast to the surrounding brightly radiating corona. Consider it like a pot of boiling water, one with a tightly fitting lid and one without. The lidded pot traps the steam, keeping its contents hot and vigorously boiling. Remove the lid, and the steam escapes, causing the pot to cool. The coronal hole is analogous to the region where the magnetic lid has been effectively removed, allowing a portion of the solar atmosphere to vent directly into space. Coronal holes exhibit various forms and understanding. These distinctions is key to predicting their varying impacts on Earth. The most stable and longest lasting are polar coronal holes. These form near the Sun's north and south magnetic poles, and can persist for months or even years during periods of low solar activity. Because of their high solar latitudes, the high-speed solar wind they produce generally streams off into space at angles that largely miss Earth, which orbits in the plane of the solar equator. More problematic for our planet are equatorial coronal holes, and especially transequatorial coronal holes. These develop at lower latitudes and can span the solar equator entirely. When such a hole rotates to face Earth, which occurs as the Sun spins on its axis once every 27 days, the high-speed solar wind streams directly toward our world. The fast solar wind from these geo-effective holes can persist for days or even weeks, as the hole maintains its position relative to Earth during each solar rotation. There is also a category known as satellite holes, smaller coronal holes at lower latitudes that maintain magnetic connections to the larger polar holes through narrow corridors of open field lines. Satellite holes can produce variable fast solar wind streams that repeatedly sweep across Earth, complicating efforts to forecast space weather. The sheer size of coronal holes varies enormously. Small holes may span only a few tens of thousands of miles. However, the giant trans-equatorial holes that have dominated recent space weather news stretch 500,000 miles or more, large enough to swallow dozens of Earths. Generally, larger holes generate faster and denser solar wind streams, which in turn cause more significant geomagnetic disturbances when they reach Earth. Coronal holes are intimately linked to the overarching solar cycle. During solar minimum, when the sun is relatively quiet and sunspots are rare, large polar coronal holes tend to dominate. The sun's magnetic field during these periods is comparatively simple, with clearly defined north and south magnetic poles. The open field regions cluster near these poles, and the resulting high-speed solar wind flows predominantly toward the outer solar system, rather than directly toward Earth. As the sun approaches solar maximum, everything becomes more chaotic. The magnetic field grows increasingly complex as new active regions emerge. Sunspots proliferate across the solar surface. The polar coronal holes may shrink or fragment. But intriguingly, equatorial and transequatorial coronal holes can appear, sometimes reaching enormous sizes even as overall solar activity intensifies. This is precisely what has surprised scientists during solar cycle 25. The giant coronal holes observed in 2024 and 2025 were not anticipated at this particular stage of the cycle. After solar maximum during the descending phase, coronal holes typically become more common and larger again, as the magnetic field simplifies and the new polarity establishes itself at the poles. Open field regions expand a period lasting several years as the sun transitions toward the next minimum, often producing recurring high-speed solar wind streams that sweep past Earth with each solar rotation. The solar wind itself merits a closer examination. This continuous outflow of charged particles, predominantly protons and electrons, was theoretically predicted by the pioneering physicist Eugene Parker in 1958. Many of his colleagues were skeptical, but measurements from early spacecraft definitively proved him correct. The solar wind streams outward in all directions from the sun, filling interplanetary space and creating what we call the heliosphere, a vast bubble of solar influence extending far beyond the orbit of Pluto. Not all solar wind is created equal. The slow solar wind, typically originating from regions of closed magnetic field lines near the sun's equator, travels at roughly 300 to 400 kilometers per second. In contrast, the fast solar wind emerging from coronal holes, where magnetic field lines open directly into space, can reach speeds of 700 to 800 kilometers per second or even higher. When these two streams interact with faster wind overtaking slower wind ahead of it, complex structures called corrotating interaction regions, CIRs, form. These regions can significantly enhance the geomagnetic effects when they eventually reach Earth. The plasma emerging from coronal holes carries embedded within it the magnetic field of the sun. This interplanetary magnetic field, IMF as it's known, has a specific polarity, meaning it points either toward or away from the sun, depending on which hemisphere of the sun the wind originated from. Coronal holes themselves also possess a polarity. A positive polarity hole has magnetic field lines pointing outward from the sun, while a negative polarity hole has field lines pointing inward. When the polarity of the incoming solar wind opposes Earth's own magnetic field orientation, a southward IMF component, a process called magnetic reconnection, becomes more efficient, transferring more energy into our magnetosphere and producing stronger geomagnetic storms. Modern instruments aboard spacecraft like SOHO's Solar Wind Ion Composition Spectrometer and the Advanced Composition Explorer ACE have enabled scientists to meticulously study the chemical composition and temperature of solar wind from different sources. Fast solar wind originating from coronal holes exhibits distinct signatures: lower ionization states, reduced heavy ion abundances, and specific velocity distributions that reveal the acceleration mechanisms at work near the Sun. The study of coronal holes has entered a new era with the Parker Solar Probe and Solar Orbiter missions. Parker has boldly flown directly through coronal hole interiors during its closest approaches to the Sun, providing the first direct in situ measurements of plasma conditions in the very regions where fast solar wind originates. The spacecraft has detected structures called switchbacks, dramatic reversals of the magnetic field that suggest complex dynamics in the acceleration of solar wind. Solar Orbiter, with its suite of remote sensing instruments, has revealed small-scale jets, sometimes called picoflares,
Thank God, we are
within
clear.
polar coronal holes that may contribute both to the heating of the corona and the acceleration of the solar wind. Despite decades of intensive study, mysteries persist. Why does the corona achieve temperatures hundreds of times hotter than the solar surface? What are the exact mechanisms that accelerate the fast solar wind to such extreme velocities? How do coronal holes form and evolve with such variability? What determines whether a coronal hole will remain stable for months or dissipate within days? These profound questions continue to drive ongoing research programs at observatories and space agencies worldwide. Planned missions like NASA's multi-slit Solar Explorer MUSE, anticipated for launch around 2027, will study the corona using advanced spectrographic techniques to measure plasma temperature, speed and turbulence at unprecedented resolution. Understanding coronal holes and the powerful solar wind they produce is paramount for predicting space weather, with sufficient accuracy to safeguard our satellites, power grids and astronauts. For those of us observing from Earth, coronal holes present a fascinating duality. They are in essence absences regions where something is missing plasma that has fled light, that has dimmed, yet their effects are profoundly present. When a giant coronal hole rotates to face our world, we feel its influence in disrupted communications, stressed power systems, expanded auroral zones, and perhaps even trembling faults deep beneath our feet. The dark patch on the Sun is not merely a void, it is a doorway, an opening through which our star breathes its atmosphere into space. And when that breath is pointed directly at us, we would do well to pay attention. Chapter 3, The Star's Rhythmic Heartbeat. Long before humanity comprehended that the Sun was a star, long before we conceived of magnetic fields or the astounding process of nuclear fusion, astute observers noticed something peculiar. Dark spots would appear on the face of the Sun, grow shift position, and eventually fade away. Ancient Chinese chronicles record such observations as early as 800 BCE. Greek philosophers debated the significance of these blemishes on a celestial body, presumed to be perfect and unchanging. But it was not until the early 17th century when Galileo Galilei daringly turned his nascent telescope towards the Sun that the systematic study of sunspots truly began. What Galileo saw challenged every established belief in Europe regarding the heavens. Dark patches, irregular in shape, distinctly moving across the solar disk as the Sun rotated. Some lingered for weeks before vanishing, while others appeared suddenly in regions that had been clear just days before. The Sun was not a flawless sphere of divine fire. It was dynamic, mutable subject to forces no one yet understood. Over the subsequent centuries, astronomers diligently accumulated observations. The German pharmacist Heinrich Samuel Schwabe, driven by an almost obsessive dedication, spent 17 years meticulously tracking sunspots, sketching the solar disk day after day between 1826 and 1843. His unwavering persistence revealed a pattern no one had ever suspected. Sunspot numbers consistently rose and fell in a regular rhythm, peaking roughly every 10 years before declining to minimum levels. Schwabe had discovered the fundamental solar cycle. Further refinements eventually pinpointed the average length at approximately 11 years, though individual cycles can vary from as short as 9 years to as long as 13. The Swiss astronomer Rudolf Wolf later standardized methods for counting sunspots, and painstakingly reconstructed historical records back to 1755, which now officially marks the beginning of Solar Cycle 1. We are currently immersed in solar cycle 25, which commenced in December 2019 and is projected to continue until around 2030. But what fundamental mechanism drives this 11-year heartbeat? Why does our star pulse between quiet phases characterised by few or even no sunspots and active phases, where the solar surface erupts with dozens of dark patches, explosive flares and colossal billion-ton ejections of plasma? The answer lies deep within the sun's magnetic field and its extraordinary dynamic behaviour. Unlike Earth, which possesses a relatively stable magnetic field generated by its solid iron core and liquid outer core, the sun generates its immense magnetic field through a complex process called the solar dynamo. The sun is not solid. It is a vast sphere of plasma that rotates, but crucially it does not rotate uniformly. Its equator completes one rotation in about 25 Earth days, while regions nearer the poles take closer to 35 days. This differential rotation stretches and twists the sun's initial magnetic field lines, which initially run from pole to pole. Imagine taking a rubber band stretched between the top and bottom of a spinning sphere, then spinning the middle of that sphere faster than its ends. The rubber band would inevitably wrap around the equatorial regions, becoming increasingly wound and distorted. This is essentially what happens to the sun's magnetic field. Over a period of years, the poloidal field, running from north to south, gradually transforms into a toroidal field wrapped around the sun's interior, like coils around a massive cylinder. These concentrated magnetic field lines eventually become unstable. They rise buoyantly through the solar interior, eventually puncturing the surface in paired loops that we observe as sunspot groups. Sunspots appear dark because the intense magnetic fields within them actively suppress convection, preventing hotter plasma from welling up from below. The result is a region roughly 3,000 degrees Fahrenheit cooler than the surrounding photosphere, still blazing at nearly 7,500 degrees Fahrenheit, but cool enough to appear black by stark contrast. The magnetic polarity of sunspot pairs follows predictable rules first discovered by the American astronomer George Ellery Hale in the early 20th century. In each hemisphere, the leading sunspot in a pair, the one positioned ahead in the direction of rotation, exhibits a consistent magnetic polarity throughout a given solar cycle. The trailing spot in the pair possesses the opposite polarity. Furthermore, this orientation is completely reversed between the northern and southern hemispheres. If northern leading spots are positive in one cycle, then southern leading spots will be negative. And here's where the story becomes even more remarkable. When the next 11-year cycle commences, everything flips. Leading spots in the north that were positive now become negative. Southern leading spots switch from negative to positive. The sun's entire global magnetic polarity is reversed. What was the magnetic North Pole is now the magnetic South Pole, and vice versa. This implies that the true full cycle of the sun's magnetic field is not 11 years, but approximately 22 years. After 2 activity cycles, the sun returns to its original magnetic configuration. This 22-year period is sometimes referred to as the Hale cycle, honouring the scientist who uncovered these crucial polarity rules. Solar maximum designates the period when sunspot numbers peak and solar activity is most intense. During maximum, the sun's magnetic field is chaotic, with field lines tangled across multiple active regions. Solar flares become frequent and powerful. Coronal mass ejections, CMEs, blast billions of tons of plasma into space. The corona itself changes shape, becoming more irregular as streamers and active region loops dominate the view. Solar minimum, in contrast, is the quiet phase. Sunspots may be entirely absent for weeks or even months. The magnetic field simplifies with clear polar regions of opposite polarity. Coronal holes expand near the poles. The corona takes on a more symmetric appearance. Solar flares and coronal mass ejections become rare. The transition from minimum to maximum takes approximately 4 to 5 years. Activity builds gradually at first, then accelerates. New sunspots initially appear at higher latitudes, then progressively migrate toward the equator. As the cycle advances, a pattern visually represented in what scientists call the butterfly diagram. because the latitude versus time plot of sunspot positions strikingly resembles a butterfly's wings. The transition from maximum back to minimum also spans several years, but it tends to be more gradual. The descending phase is notably characterised by the increasing prominence of coronal holes, particular equatorial ones that can persist through multiple solar rotations. This is the period when recurring high-speed solar wind streams are most common, sweeping past Earth every 27 days, as the same coronal hole rotates back into a geo-effective position. Not all solar cycles are created equal. Some solar maximums produce far more sunspots and intense activity than others. Scientists utilise the smooth sunspot number, a 13-month average that effectively reduces short-term fluctuations to compare cycle strength. The strongest cycle ever recorded in the modern era was cycle 19, which peaked in 1958, with a smooth sunspot number exceeding 200. The weakest in the modern era was cycle 24, which peaked in April 2014, with a maximum around 116, well below the historical average of approximately 179. The prediction for solar cycle 25, released by an international panel, convened by NOAA, NASA and the International Space Environmental Services in December 2019, forecasted yet another weak cycle, with a maximum of about 115 sunspots around July 2025. This prediction aligned with the trend of weakening cycles that had characterised cycles 21 through 24. Some researchers even speculated that the Sun might be heading towards a grand minimum, an extended period of very low activity, similar to the Maunder minimum of 1645 to 1715, when sunspots nearly disappeared for 70 years. The prediction, however, was fundamentally wrong. By 2022, just 2 years into the cycle, observed sunspot numbers were already significantly exceeding forecasts. Activity ramped up far faster than anyone expected. By October 2023, NOAA issued a revised prediction, calling for an earlier and stronger peak, possibly reaching smooth sunspot numbers between 137 and 173, sometime between January and October 2024. In October 2024, NASA and NOAA officially declared that the Sun had indeed reached solar maximum. The smooth sunspot number had climbed to approximately 161. Solar cycle 25 was not just stronger than predicted, it had proven to be significantly more active than its predecessor cycle 24. And the surprises continued even after the official declaration of maximum activity remained high. In November 2025, the Sun unleashed an X5.16 solar flare, the strongest of the cycle, and the sixth most powerful in all of solar cycle 25. Coronal holes that should have been more typical of the descending phase appeared at enormous sizes even while the Sun was still near peak activity. Scientists now actively debate whether we have truly passed the maximum or whether solar cycle 25 might produce a secondary peak. Some cycles in history have exhibited double maxima, with two distinct peaks of activity separated by a year or more. The data through late 2025 shows hints that this could be occurring, though only time will definitively reveal the true shape of the cycle. Why does any of this matter beyond academic curiosity? Because the solar cycle fundamentally controls the rhythm of space weather that impacts our planet. During solar maximum, geomagnetic storms become more frequent and more intense. The radiation environment in space becomes significantly more hazardous for astronauts and sensitive spacecraft electronics. Satellite operators face increased atmospheric drag and heightened debris tracking challenges. Power grid operators must maintain constant vigilance for geomagnetically induced currents. Airlines reroute polar flights to avoid radiation exposure and communication blackouts. Conversely, during solar minimum, the immediate risks diminish. They do not disappear entirely. Cosmic rays from outside the solar system penetrate more easily when the Sun's magnetic field is weak, slightly increasing radiation exposure at high altitudes. And the coronal holes that grow during the descending phase and minimum continue producing high-speed solar wind streams that can still trigger significant geomagnetic storms. Even when the sun appears quiet, the 11-year heartbeat of our star is not merely an astronomical curiosity. It is a fundamental rhythm that profoundly shapes the space environment in which our entire technological civilization exists. Understanding it, predicting its variations, and preparing for its fluctuations has become absolutely essential for a species that has wrapped itself in satellites, power grids, and global communication networks. The sun will continue pulsing through its cycles for billions of years to become an eternal cosmic drumbeat. Our challenge, our collective human endeavour, is to learn its rhythms well enough to dance safely within them, to adapt and innovate in the face of its inherent dynamism. Chapter 4, Solar Wind and the Invisible River. In 1958, a brilliant young physicist named Eugene Parker proposed something truly radical, a theory that defied conventional wisdom. He suggested that the sun was not simply radiating light and heat into an empty vacuum. Instead, he argued it was continuously exhaling streaming charged particles outward at tremendous velocities, filling the entire solar system with a thin yet constant flow of solar material. He named this continuous outflow the solar wind. His colleagues reacted with deep skepticism, some even with hostility. The idea that plasma could continuously escape the sun's immense gravity and pervade interplanetary space seemed to contradict fundamental thermodynamic principles. One prominent scientist famously recommended that Parker's groundbreaking paper be rejected from publication. However, the visionary editor of the Astrophysical Journal chose to publish it anyway, and within just 4 years, both the Soviet Luna 1 and American Mariner 2 spacecraft launched into space, unequivocally confirming that Parker had been right all along. The solar wind is real. It is pervasive, and it fundamentally shapes the vast expanse of space through which all planets, including our own, majestically move. To truly understand the solar wind, one must first appreciate the extraordinary temperatures of the solar corona. While the visible surface of the sun, the photosphere, registers at a searing 500 degrees Celsius, the corona itself reaches temperatures of an astounding 1 to 3 million degrees Celsius. At such extreme temperatures, the thermal energy of individual particles dramatically exceeds the gravitational binding energy of the sun. They can and do escape, and escape they do in numbers far beyond ordinary human comprehension. Every single second, the sun loses approximately 1 million tons of material to this relentless solar wind. That sounds like an enormous amount, and indeed it is by any human measure. Yet the sun contains roughly 2,000 trillion tons of matter. At the current rate of loss, it would take an unimaginable 150 billion years for the solar wind to carry away even 1% of the sun's total mass. Our star, in its cosmic generosity, can well afford to be so liberal with its outflow. The composition of the solar wind closely mirrors the composition of the sun itself. Approximately 95% of it consists of protons, which are the nuclei of hydrogen atoms. Another 4% comprises alpha particles, essentially helium nuclei containing 2 protons and 2 neutrons. The remaining 1% includes heavier ions, electrons, and trace amounts of other elements. All of these particles constitute a highly electrically conductive gas intricately threaded with magnetic field lines. These magnetic field lines are absolutely crucial to the story. As solar wind plasma streams outward from the sun, it carries embedded within it the magnetic field of the solar corona. This interplanetary magnetic field, often abbreviated as IMF, does not simply point straight outward. Because the sun actively rotates, while the plasma continuously flows outward, the field lines curve into a characteristic spiral pattern, much like water spraying from a spinning garden sprinkler. This elegant pattern is known as the Parker spiral, named of course after Eugene Parker, who brilliantly predicted both the solar wind and its intricate magnetic architecture. At Earth's orbit, a staggering 93 million miles from the Sun, the Parker spiral typically makes an angle of roughly 45 degrees with respect to the Sun-Earth line. The magnetic field lines have wound around enough to be significantly tilted from the purely radial direction. This specific geometry holds immense significance. because the orientation of the interplanetary magnetic field profoundly affects how the solar wind interacts with Earth's protected magnetosphere. Not all solar wind travels at the same speed. The slow solar wind, typically originating from regions of closed magnetic loops near the Sun's equator, moves at a speed of 300 to 400 kilometers per second. In contrast, the fast solar wind streaming from coronal holes, where magnetic field lines open directly into space, can reach speeds of 600 to 800 kilometers per second or even faster. At these velocities, it takes the slow solar wind approximately 4 to 5 days to reach Earth, while the fast solar wind can arrive in a mere 2 to 3 days. When fast solar wind streams catch up with slower solar wind ahead of them, the two streams dynamically interact, creating compressed regions of higher density and stronger magnetic fields. These are called corrotating interaction regions, CIRs. These complex structures spiral through the solar system along with the Parker spiral, and can significantly enhance geomagnetic effects when they sweep past Earth. During the descending phase of the solar cycle, when coronal holes are common and persistently active, corrotating interaction regions become a regular and predictable feature of space weather. The solar wind does not simply cease at Earth's orbit. It continues its outward journey past Mars, past Jupiter, past Saturn, and far beyond the orbit of Pluto until it eventually encounters the interstellar medium, the thin gas and dust existing between the stars. This remote boundary region is called the heliopause, located roughly 120 astronomical units from the Sun, which equates to about 11 billion miles. Within this vast bubble known as the heliosphere, the solar wind exerts its dominant influence. Beyond it lies true interstellar space, a cosmic territory explored only by the pioneering Voyager 1 and 2 spacecraft. The solar wind creates and meticulously maintains this heliosphere, effectively acting as a protected zone within our galaxy. Cosmic rays, high-energy particles accelerated by distant supernovae, and other violent celestial events constantly bombard the heliosphere from outside. The magnetic field carried by the solar wind deflects and modulates many of these cosmic rays, significantly reducing the radiation environment throughout our solar system. When solar activity is high and the solar wind is strong, fewer cosmic rays penetrate to Earth's orbit. Conversely, when solar activity is low, more people manage to get through. But it is the direct interaction with Earth's magnetic field that most immediately affects human technology and safety. Our Earth is enveloped by a magnetosphere, an expansive region of space entirely dominated by our planet's intrinsic magnetic field. This vital field is generated deep within Earth's core, where the rotation of liquid iron creates a powerful dynamo effect, similar in principle to the Sun's dynamo, but operating on vastly different scales and conditions. The magnetosphere extends tens of thousands of miles into space on the day side facing the Sun, and stretches into an incredibly long tail, millions of miles long on the night side. When the solar wind arrives at Earth, it cannot simply penetrate the magnetosphere. Plasma by its very nature cannot easily cross magnetic field lines. Instead, the solar wind flows around the magnetosphere, much like water flowing around a resilient rock in a fast-moving stream. On the sunward side, it compresses the magnetosphere, pushing the boundary known as the magnetopause closer to Earth. On the nightward side, it stretches the magnetosphere into its characteristic elongated tail. The pressure exerted by the solar wind directly determines the position of the magnetopause. Under normal conditions, this critical boundary sits roughly 10 Earth radii from the surface, about 40,000 miles. However, during periods of exceptionally high solar wind pressure, such as when a high-speed stream from a coronal hole impacts Earth, the magnetopause can be pushed inward to 6 Earth radii or even less. Satellites in geostationary orbit positioned approximately 22,000 miles up can find themselves momentarily outside the crucial protection of the magnetosphere. The most significant factor in the solar wind magnetosphere interaction is not merely the speed or density of the incoming plasma, but critically the orientation of the interplanetary magnetic field. Earth's magnetic field intrinsically points northward at the equator from the South Pole toward the North Pole. When the interplanetary magnetic field has a southward component, meaning it opposes Earth's northward field, a powerful process called magnetic reconnection can occur. Magnetic reconnection is a fundamental process in plasma physics, a cosmic dance of energy release. When two magnetic field lines of opposite polarity converge, they can explosively break and reconnect in entirely new configurations, releasing tremendous amounts of energy. At Earth's day side, magnetopause reconnection between the southward interplanetary magnetic field and the northward terrestrial field effectively opens a pathway for solar wind energy to penetrate and enter the magnetosphere. This transferred energy flows along magnetic field lines toward the poles, energizes particles in the radiation belts, and ultimately drives the awe-inspiring phenomena we collectively call geomagnetic storms. The KP index mentioned in earlier chapters is one widely used measure of geomagnetic activity, resulting from this intricate solar-wind magnetosphere interaction. It is meticulously calculated from magnetometer observations at stations positioned around the world, tracking fluctuations in the magnetic field caused by electrical currents in the magnetosphere and ionosphere. The index ranges from 0, indicating very quiet conditions, to 9, signifying extreme storm levels. NOAA's Space Weather Prediction Center utilizes a simpler 5-level scale for geomagnetic storms ranging from G1 for minor storms to G5 for extreme storms. Each level corresponds to specific ranges of the KP index and carries distinctly different implications for technology and infrastructure. A G1 storm might cause minor power grid fluctuations and slightly expand the auroral zone. In stark contrast, a G5 storm could trigger widespread power outages, permanently damage critical transformers, severely disrupt satellite operations, and produce auroras visible even from tropical latitudes. The solar wind is thus far more than an astronomical curiosity. It is the fundamental medium through which our star constantly powerfully interacts with our home planet. Every moment of every day, Earth swims through this invisible river of charged particles. Most of the time, our magnetic shield effortlessly deflects the flow, maintaining our safety. But when the solar wind intensifies, when a high-speed stream from a coronal hole or a powerful shock wave from a coronal mass ejection arrives, the interaction can become violent and disruptive. Eugene Parker, who sadly passed away in 2022 at the age of 94, lived to witness his theoretical prediction confirmed beyond any doubt. He saw spacecraft venture directly into the solar wind and meticulously measure its properties. He even witnessed the historic launch of the Parker Solar Probe, the first NASA mission ever named for a living person, which now courageously flies closer to the Sun than any human-made object in history. The invisible river continues to flow. It has flowed for 4.5 billion years, ever since the Sun first ignited in the collapsing cloud of gas and dust that gave birth to our solar system. It will continue flowing for billions of years more until the Sun eventually exhausts its hydrogen fuel, swells into a red giant, ultimately shedding its outer layers and becoming a white dwarf. For now, in our fleeting moment, we meticulously learn to read the river's currents and predict its inevitable floods. The solar wind carries the very breath of our star to every corner of the heliosphere. Understanding that breath and profoundly respecting its immense power is no longer optional for a technological civilization. It is quite simply essential for our survival and progress. Chapter 5, When Our Shield Trembles, Vulnerability in a Cosmic Storm. On March the 13th, 1989, a cosmic tempest struck with brutal efficiency. The Sun, without warning, hurled a colossal cloud of plasma and an entangled magnetic field towards Earth. This coronal mass ejection journeyed through the vacuum of interplanetary space for 3 days before slamming into our planet's magnetosphere with devastating force. Within a mere 90 seconds of the impact, 6 million people across Quebec were plunged into darkness as the Hydro-Quebec power grid completely collapsed. Transformers overloaded, circuit breakers tripped in cascading failures, and the entire province went dark for 9 long hours. Hospitals scrambled to activate backup generators, Traffic signals failed, heating systems shut down on a night when temperatures plummeted well below freezing, and businesses ground to a halt. A modern, technologically advanced society suddenly discovered just how profoundly vulnerable it had become to events unfolding 93 million miles away. The March 1989 geomagnetic storm was indeed severe, but by historical standards it was not exceptional. It registered approximately 589 nanoteslas on the DST index, a measure of the depression in Earth's magnetic field caused by the intensification of the ring current during storms. This placed it among the stronger storms of the 20th century, but still nowhere near the most powerful ever recorded. That distinction belongs to events from an era before our pervasive technological dependencies transformed space weather into a matter of critical national and global concern. Yet even in 1989, the Quebec blackout served as an undeniable demonstration. Modern infrastructure exists precariously within the reach of solar fury. To truly comprehend how geomagnetic storms inflict damage on power grids and disrupt technology, we must examine the dramatic shift in dynamics when the solar-wind magnetosphere interaction intensifies beyond normal levels. Under ordinary conditions, Earth's magnetic field effectively deflects most of the solar wind around the planet. Magnetic reconnection occurs at modest rates, and the energy entering the magnetosphere dissipates without major incident. But when a powerful coronal mass ejection CME arrives, or when a particularly fast and dense solar wind stream from a coronal hole slams into the magnetopores, the dynamics transform dramatically, unleashing a torrent of energy. Coronal mass ejections are fundamentally different from the steady flow of solar wind. These are explosive releases of billions of tons of plasma and tangled magnetic fields blown outward from the sun at staggering velocities ranging from a few hundred to over 2,000 kilometers per second. The fastest CMEs can reach Earth in under 24 hours, though a typical transit takes 2 to 3 days. When they arrive, they often carry magnetic fields far stronger than the ambient solar wind. Crucially, these embedded fields can be oriented strongly southward, maximising the conditions for magnetic reconnection and energy transfer. The arrival of a CME at Earth typically unfolds in stages. First comes the shock wave, the leading boundary, where the fast-moving CME plasma has compressed the slower solar wind ahead of it. This sudden compression pulse triggers what is known as a storm sudden commencement, a sharp increase in the magnetic field strength recorded at ground stations worldwide. The magnetosphere is forcefully squeezed, and currents flowing in the magnetopores intensify. Behind the shock wave comes the sheath region, a turbulent zone of compressed plasma situated between the shock and the CME proper. Sheath regions often contain highly variable magnetic fields, including significant southward components that can drive substantial reconnection and storm development even before the main CME structure arrives. Finally, the magnetic cloud or ejector itself, the core of the CME, arrives. This region typically exhibits smoothly rotating magnetic fields and lower plasma temperatures. If the magnetic field within the cloud is oriented southward for extended periods, it can drive prolonged and intense geomagnetic storming. As reconnection relentlessly proceeds on the day side, magnetopore's magnetic flux is transferred to the night side magnetotail. Energy accumulates within this tail until instabilities trigger explosive reconnection there, as well releasing the stored energy into the inner magnetosphere. Particles are accelerated to incredibly high energies and injected into the ring current, a belt of charged particles encircling Earth at distances of 3 to 8 Earth radii. The ring current generates its own magnetic field, opposing Earth's intrinsic field at low latitudes. This is precisely what the DST index measures. During intense storms, the ring current can become so powerful that it measurably reduces the surface magnetic field by hundreds, or even over 1,000 nanoteslas. This significant depression in field strength serves as a direct indicator of the immense energy that has been pumped into the magnetosphere from the solar wind. Meanwhile, powerful electric currents also flow within the ionosphere, the electrically conducting layer of Earth's upper atmosphere. Auroral electrojets, intense horizontal currents flowing within the auroral zones, can exceed millions of amperes during major storms. These rapidly varying currents through the principle of electromagnetic induction, the same fundamental principle that makes transformers work, induce electric fields at Earth's surface. And this is precisely where human infrastructure becomes acutely vulnerable. Long conductive networks such as power lines act like giant antennas for these induced electric fields. Currents specifically called geomagnetically induced currents, GICs, flow through the grounded neutrals of transformers seeking paths through the interconnected power grid. These are quasi-direct current flows fundamentally different from the alternating current the grid is designed to handle. Transformers are particularly susceptible to these rogue currents. GICs can saturate transformer cores, causing them to operate inefficiently, generate excessive heat, and produce harmonic distortions in the power signal. In mild cases, this merely degrades power quality. In severe cases, transformers can overheat and suffer permanent irreparable damage. The failure of even a few critical high-voltage transformers can cascade through interconnected grids, leading to widespread and prolonged blackouts. The Quebec collapse in 1989 demonstrated this vulnerability dramatically. Within 90 seconds of the storm's intensification, relays tripped across the entire Hydro-Quebec system. The utility had no time to respond. The province's grid was down before operators fully grasped what was happening. Recovery took hours. Had more transformers been permanently damaged, recovery could have taken weeks or even months, highlighting a critical fragility in our modern systems. Since 1989, modern power grids have implemented some protective measures. Operators now diligently monitor space weather forecasts and can take precautions during predicted storms, such as cancelling non-essential maintenance, increasing power reserves, and preparing for potential load shedding. Some utilities have even installed GIC blocking devices on their most vulnerable transformers. However, the fundamental vulnerability remains. A sufficiently powerful storm will inevitably overwhelm existing protections, a critical strategic risk. Power grids are not the only concern. Geomagnetic storms impact satellites in multiple ways. Enhanced radiation levels can damage sensitive electronics and degrade solar panels, shortening satellite lifespans. Increased atmospheric drag at low Earth orbit altitudes causes satellites to lose altitude faster than expected, requiring more frequent and costly orbital maneuvers to prevent re-entry or collisions. Thousands of satellites now populate low Earth orbit, including massive mega constellations like Starlink. During the May 2024 geomagnetic storm, one of the strongest in decades, satellite operators reported significant increases in drag and the urgent need for coordinated maneuvering to avoid potential collisions. GPS and other global navigation satellite systems, GNSS, rely on precisely timed radio signals passing through the ionosphere. Geomagnetic storms severely disturb the ionosphere, introducing errors that degrade positioning accuracy. During the 1989 storm, GPS errors reportedly exceeded normal levels, significantly prompting aviation authorities to issue warnings about reduced navigation reliability. High-frequency HF radio communications, essential for aircraft traversing oceanic and polar routes, can be completely blocked during major storms. When the ionosphere is severely disturbed, radio signals that normally reflect off this layer and travel beyond the horizon instead become absorbed or scattered. Aircraft lose contact with ground controllers and emergency communications become unreliable precisely when they might be most desperately needed. The radiation environment in space intensifies dramatically during geomagnetic storms. Particles accelerated to high energies can penetrate spacecraft shielding, damaging sensitive electronics or posing severe radiation hazards to astronauts. During the largest storms, crew aboard the International Space Station ISS may be instructed to shelter in more heavily shielded portions of the station. Future crewed missions to the Moon and Mars will require robust plans for dealing with space weather emergencies far from Earth's protective magnetosphere. Oil and gas pipelines, which can stretch for hundreds or thousands of miles across continents, also experience geomagnetically induced currents. While pipelines are not as acutely vulnerable as power transformers, GICs can accelerate corrosion at points where the currents enter or exit the metal structure. Over time, repeated exposure to GICs can compromise pipeline integrity, potentially leading to leaks or catastrophic failures, a subtle but insidious long-term threat. The deeply interconnected nature of modern infrastructure creates additional compounding risks. A widespread power outage can rapidly cascade into failures of water treatment plants, emergencies at hospitals, breakdowns in communication networks, and severe disruptions to transportation systems. Financial systems utterly dependent on electronic transactions can be paralysed. The downstream effects of a major geomagnetic storm extend far beyond the immediate electrical impacts threatening the very fabric of society. NASA, the European Space Agency, and other international organisations maintain vast fleets of spacecraft to continuously monitor the sun and the solar wind, providing critical early warnings of incoming disturbances. Satellites positioned at the Lagrange point about 1 million miles south of Earth can detect CME arrivals typically 15 to 45 minutes before they reach Earth. This warning time allows for some immediate protective actions, but it is often far too short for many comprehensive preparations. The overarching goal of space weather research is to extend these warning times and dramatically improve forecast accuracy. New missions, more sophisticated models, and an enhanced understanding of Sun-Earth connections all contribute to this vital effort. But the fundamental reality remains Earth orbits within the dynamic, sometimes tempestuous atmosphere of an active star. And that star occasionally reminds us of our inherent vulnerability with storms that can overwhelm our technological shields. When the next great storm inevitably comes, will we be ready? The answer hinges directly on the investments we make today in monitoring, forecasting, and hardening our critical infrastructure. The shield has faltered before, it will falter again. The question is not if but when, and whether we will be caught off guard or prepared to weather the solar fury with resilience and foresight. Chapter 6. Echoes of a Cosmic Storm, the Carrington Legacy. The morning of September 1st, 1859, dawned like any other, at least for a time. For Richard Carrington, a wealthy English amateur astronomer who had built a private observatory at Red Hill south of London, it began with routine dedication. He pursued his passion for solar observation with the meticulous discipline of a professional scientist. Each clear day he projected a magnified image of the sun onto a screen and carefully sketched the precise positions and intricate shapes of sunspots, painstakingly building a record that would profoundly contribute to humanity's nascent understanding of the solar cycle. Shortly before noon, as Carrington meticulously traced the outlines of a particularly large sunspot group, something utterly unprecedented occurred. Two intensely brilliant patches of white light erupted within the sunspot region, blazing incandescently against the already luminous solar disk. Carrington was so startled by the sudden unexpected brilliance that he instinctively rushed to find a witness. But by the time he returned barely a minute later, the extraordinary lights were already fading. The entire dramatic event lasted approximately 5 minutes. Carrington had just witnessed the first definitively recorded observation of a solar flare.
Geomagnetic-induced currents detected in Trans-Siberian pipelines.
Independently, another keen English astronomer named Richard Hodgson observed the very same phenomenon from his own observatory. Both men promptly published their observations in the monthly notices of the Royal Astronomical Society, their accounts appearing side by side in the November 1859 issue. They had documented something no human had ever recorded before: an explosive release of energy of unimaginable scale on the surface of our sun. However, Carrington, with admirable scientific caution, remained hesitant about drawing premature conclusions. In his report, he noted that a significant magnetic disturbance had occurred on Earth the following day, but famously wrote that one swallow does not make a summer. He suspected a connection and intuition born of careful observation, but he knew that a single coincidence did not constitute definitive proof. What Carrington could not possibly have known was that the flare he had observed was inextricably associated with a massive coronal mass ejection CME, a billion-ton cloud of magnetized plasma that was already hurtling toward Earth at an extraordinary, unprecedented speed. This powerful CME reached our planet in just 17.6 hours of transit time, so incredibly fast that it remains exceptional even by modern standards. Typical CMEs take 2 to 4 days to reach Earth. The Carrington CME travelled at an astonishing nearly 2,400 kilometers per second. When it arrived on September 2, 1859, the sheer force of its impact triggered the most intense geomagnetic storm in recorded history, a cosmic event that reverberated across the globe. The effects were felt worldwide. Telegraph systems, the cutting-edge communication technology of the era, went completely haywire. Operators reported sparks leaping from their equipment. Some even received painful electrical shocks. In several telegraph offices, the paper itself caught fire from the induced currents, a terrifying testament to the power of the invisible forces at play. Yet paradoxically, some telegraph lines continued to operate, even after operators had disconnected their batteries powered solely by the geomagnetically induced currents flowing through the wires. One telegraph operator in Pittsburgh reported that the weights of his register were lifted by the sheer strength of the current. Another in Boston found he could communicate with Portland, Maine using only the auroral current, no battery required.
Seismic sensors.
Messages sent under these surreal conditions were reportedly clear and perfectly readable. The Earth itself had for a brief, bewildering period become a direct power source. The auroral displays that accompanied the storm were perhaps the most spectacular ever witnessed by modern humanity. The northern lights, normally confined to high latitudes, swept across the entire northern hemisphere with breathtaking intensity. Auroras were observed in Cuba, Hawaii, and as far south as Colombia and Panama. In the southern hemisphere, the aurora australis was seen from Chile, Australia, and reportedly from ships at sea near the equator. The light was so intensely bright that people awoke in the night genuinely believing that dawn had arrived prematurely. In the Rocky Mountains, bewildered gold miners reportedly began preparing breakfast, completely fooled by the aurora's brightness into thinking morning had come. Newspapers reported that residents of the northeastern United States could read by the light of the aurora alone, a surreal experience that fused the terrestrial with the cosmic. The sky glowed in vibrant curtains of red, green and purple colours, dancing and shifting in patterns that terrified some observers and utterly enchanted others. Contemporary accounts describe the aurora as filling the entire sky from horizon to horizon. Some witnesses compared it to the sky itself being on fire. Others described sheets and curtains of light rippling overhead, a dynamic spectacle unlike anything seen before or since. The phenomenon persisted for hours, far longer than typical auroral displays, reflecting the sustained extreme intensity of the geomagnetic storm. Scientific instruments of the era, though rudimentary by today's standards, captured quantitative evidence of the storm's power. Magnetometers at observatories worldwide recorded extreme fluctuations. The Kew Observatory in London documented what is now interpreted as a magnetic crochet, a sudden disturbance in the magnetic field occurring simultaneously with the solar flare itself caused by increased ionization in the upper atmosphere from the flare's X-ray and ultraviolet emissions. The main storm phase produced magnetic field depressions estimated at over 1/700 nanoteslas, based on meticulous reconstructions from surviving records. For comparison, the March 1989 storm that blacked out Quebec reached approximately 589 nanoteslas. The Carrington Event was by this measure roughly 3 times more intense, an almost unimaginable level of geomagnetic fury. Scientists have since studied the Carrington Event extensively, attempting to understand the precise conditions that made it so extreme and, crucially, what the catastrophic consequences would be if a similar storm were to strike today. The emerging picture is profoundly sobering. The Carrington CME was likely preceded by another CME a day or two earlier. This prior eruption may have cleared the interplanetary medium of slower solar wind, effectively carving out a partially evacuated channel, allowing the Carrington CME to travel through it at exceptional unimpeded speed. When it arrived at Earth, its magnetic field was oriented strongly southward for an extended period, maximising the efficiency of magnetic reconnection and the transfer of immense energy into the magnetosphere. In 1859, the world's technological infrastructure consisted primarily of telegraph networks. These were indeed vulnerable to geomagnetically induced currents, but the damage was relatively limited mostly to equipment. Operators could disconnect batteries, wait out the storm, and resume operations. Today, the situation is vastly frighteningly different. Studies commissioned by the US National Academy of Sciences and other prominent bodies have attempted to rigorously estimate the devastating impact of a Carrington-class storm on modern infrastructure. The results are nothing short of alarming. Power grids across North America and Europe could experience widespread simultaneous transformer failures. Unlike the Quebec event of 1989, where a handful of transformers failed and were replaced within weeks, a Carrington-level storm could permanently damage hundreds of high-voltage transformers simultaneously. These critical transformers are not mass-produced, readily available items sitting in warehouses. They are custom manufactured, often overseas, with lead times of 1 to 2 years. If hundreds failed at once, the replacement process would take years, not weeks. Areas without power for extended periods would face cascading failures in absolutely essential services, water treatment, sewage systems, food distribution, medical care, and crucially public order. The National Academy study estimated that a severe geomagnetic storm could cause economic damage exceeding $2 trillion in the United States alone during the first year, an unimaginable cost. Recovery could stretch over 4 to 10 years, fundamentally altering national economies and supply chains. Some researchers consider even these estimates conservative, a chilling thought. Satellites, the very backbone of modern global communication, navigation and surveillance, would face extreme radiation environments. Many would likely be damaged or destroyed beyond repair. GPS navigation, on which everything from aviation to agriculture, from logistics to financial transactions now depends, could be severely degraded or rendered completely unavailable for extended periods, crippling countless industries. Communication satellites could fail en masse. The internet, increasingly reliant on satellite links and vulnerable ground infrastructure, could experience major disruptions, fracturing global connectivity. The probability of a Carrington-class event is difficult to assess precisely, but it is certainly not negligible. On July 23, 2012, a CME of Carrington-class intensity erupted from the Sun. By pure cosmic chance, it was directed away from Earth, missing our planet by approximately 9 days of solar rotation. Had the eruption occurred just a week earlier, this colossal CME would have struck Earth directly. Researchers estimate that the probability of a Carrington-class storm in any given decade ranges from approximately 10 to 12% depending on assumptions about the solar cycle and CME frequency distributions. Over a human lifetime, the odds of experiencing such an event are substantial, a risk we cannot afford to ignore. Preparations have begun, but progress remains slow and uneven. Some power utilities have installed GIC monitoring equipment and developed rudimentary emergency procedures. NOAA and its partner agencies have indeed improved space weather forecasting capabilities, a critical step forward. The Deep Space Climate Observatory DSCOVA, positioned at the L1 Lagrange point, provides 15 to 60 minutes of warning for incoming CME arrivals, offering a crucial if short window for protective actions. But fundamental vulnerabilities persist. The vast and complex power grid has not been systematically hardened against extreme space weather events. Many utilities driven by economic pressures resist expensive upgrades for an event that might not occur during their immediate planning horizon. International coordination, vital for a globally connected threat, remains limited, and standards are inconsistent, creating dangerous weak links. Richard Carrington died in 1875, never fully comprehending the monumental significance of what he had witnessed that September morning. He astutely suspected that the solar flare and the geomagnetic storm were connected, but the intricate physics that explains this connection would not be developed for another century. Today we understand that he observed a pivotal moment in the profound relationship between the Sun and Earth, a stark, humbling reminder that our star is capable of violence that can reach across 93 million miles and shake our technological civilization to its very foundations. The Carrington Event was not a unique anomaly. Ice core and tree ring studies have unveiled compelling evidence of even more powerful solar storms in the distant past. An event around 774 to 775 AD appears to have been 10 to 20 times more powerful than the Carrington storm. Another occurred around 993 to 994 AD. These Miyake events, as they are now called, will be utterly catastrophic for modern civilization, truly world-changing. We live in a technological age built on assumptions of inherent stability, assumptions that the Sun in its boundless dynamism simply does not share. The Carrington Event of 1859 stands as an enduring warning, a historical data point demonstrating that extreme space weather is not theoretical speculation, but documented reality. The question is not whether another great storm will come. The profound question is when and whether we will be truly ready to face it. Chapter 7. Earth's Tremors and Solar Whispers. The Unseen Connection. For over a century, scientists have debated a profoundly controversial question. Can events unfolding on the Sun, 93 million miles away, genuinely influence earthquakes here on Earth? The very idea seems implausible at first consideration. Earthquakes, after all, result from the gradual accumulation of immense stress along geological fault lines, stress that slowly builds over years, decades, or even centuries, until the rock suddenly fractures and violently releases its stored energy. What conceivable connection could solar activity operating on timescales of days to years possibly have with this deep, inexorable geological process? Yet the question, like a persistent tremor, refuses to disappear. It was first tentatively proposed as early as 1853 by the visionary solar astronomer Rudolf Wolf, the same scientist who meticulously standardized sunspot counting. Since then, dozens of researchers have reported intriguing correlations between solar activity and earthquake occurrence, only to be met by an equal number of studies finding no discernible connection at all. The scientific community remains deeply divided, a testament to the complexity and elusiveness of the potential link. In recent years, however, the emergence of new, higher resolution data and the application of more sophisticated statistical methods have revitalized this long-standing debate. A landmark paper published in Scientific Reports in 2020 meticulously analyzed 20 years of proton density and velocity data from the SOHO satellite alongside worldwide seismicity recorded in the ISC GM earthquake catalogue. The researchers uncovered what they called a clear correlation between proton density in the solar wind and the occurrence of large earthquakes with magnitudes greater than 5.6, with a consistent time lag of approximately 1 day. The statistical significance of this correlation was striking. The probability of the correlation being a random coincidence was calculated at less than 1 in 100,000, an exceedingly low chance. Furthermore, the correlation consistently strengthened as the magnitude threshold was raised, indicating that the largest earthquakes exhibited the strongest association with elevated proton density in the solar wind. If this compelling result holds up to further rigorous scrutiny, it suggests that the solar wind is somehow influencing the timing of major earthquakes, not causing earthquakes from scratch, which would indeed be physically implausible, but perhaps acting as the final subtle trigger for the release of stress that was already accumulated and poised to rupture. Think of it as the proverbial straw that breaks the camel's back. The camel was already overloaded. The straw simply determined the precise moment of failure. But what plausible physical mechanism could explain such an astonishing connection between cosmic winds and terrestrial tremors? several intriguing hypotheses have been proposed, and research published as recently as March 2025 continues to explore them. One prominent hypothesis involves telluric currents. When the solar wind powerfully interacts with Earth's magnetosphere, it induces electric currents not only in our vulnerable power lines, but also significantly within the crust of the Earth itself. These telluric currents flow through conductive rock layers following paths of least resistance. Some researchers have suggested that these subtle currents could slightly heat fault zones, thereby reducing the frictional strength of the rock and making slip more likely. Others propose that the currents could directly stress the rock through subtle electromagnetic effects. A second hypothesis involves the piezoelectric effect. Quartz and certain other minerals which are common constituents of Earth's crust are piezoelectric. This means they generate electric fields when subjected to mechanical stress, and conversely they experience mechanical stress when exposed to external electric fields. The reverse piezoelectric effect could translate the minute variations in the electric field caused by solar wind disturbances into tiny additional stresses along fault zones. On faults already critically near their breaking point, these seemingly insignificant additions might be just enough to initiate rupture. A third and more recent hypothesis focuses on broader thermal effects mediated by the sun's influence on Earth's climate. Research published in 2025 by scientists from the University of Tsukuba and Japan's National Institute of Advanced Industrial Science and Technology examined how solar heat affects surface temperatures, which in turn influence rock properties and groundwater movement. Temperature changes can make rocks more brittle. Changes in rainfall and snowmelt can subtly alter the pressure on fault systems. While these effects are admittedly subtle, the researchers found that including surface temperature data significantly improved earthquake forecasting models, particularly for shallow earthquakes, which are most susceptible to surface conditions. The intricate connection between solar activity and earthquakes may not operate through a single isolated mechanism, but rather through multiple subtly interconnected pathways acting simultaneously. Solar flares unleash bursts of X-rays and ultraviolet radiation that ionize the upper atmosphere. Coronal mass ejections send powerful shock waves of plasma and magnetic field that compress the magnetosphere and induce ground currents. And longer-term variations in solar irradiance affect global temperatures over multi-year timescales. All of these solar influences interact with an incredibly complex Earth system that includes our atmosphere, oceans, vast ice sheets, and the solid Earth beneath. Critics of the solar earthquake connection, and there are many, point to several significant challenges. The stress changes induced by any plausible electromagnetic or thermal mechanism are many orders of magnitude smaller than the tectonic stresses that actually cause earthquakes. How could such tiny perturbations trigger events releasing millions of times more energy than the perturbation itself? The answer may lie in the concept of criticality. A fault system near failure is exquisitely sensitive to even small disturbances. Just as a sand pile critically poised near its maximum slope can avalanche from the addition of a single grain, a fault on the verge of rupture might only need a subtle cosmic nudge. Another formidable challenge is the inherent difficulty of establishing direct causation from mere correlation. The sun exhibits clear cyclical patterns of activity. Earthquake occurrence, while seemingly random in the short term, exhibits long-term patterns related to tectonic loading. Finding correlations between two complex cyclical phenomena is relatively easy. Proving that one definitively causes the other is far harder. Statistical flukes are bound to occur, and publication bias often favours positive results, leading researchers to unconsciously choose parameters that maximise apparent correlations. Yet despite these challenges, the evidence continues to accumulate and intrigue. A study published in Geophysical Research Letters in March 2025 introduced a new statistical method called shift neighbourhood matching correlation to assess the link between intense geomagnetic storms and global strong earthquakes. The results indicated a statistically significant increase in earthquake occurrence following geomagnetic storms, with the effect becoming apparent after a time lag that varied by region. 2025 has indeed been an unusually seismically active year, with major earthquakes striking in locations around the Pacific Ring of Fire and beyond. Simultaneously, the Sun has been producing some of the largest coronal holes of the 21st century, generating repeated high-speed solar wind streams that have relentlessly buffeted Earth's magnetosphere. Is there a connection? The correlation is highly suggestive, but as always, correlation is not causation. What is becoming increasingly clear, however, is that Earth does not exist in isolated splendour. Our planet orbits and is inextricably embedded within the active dynamic atmosphere of a restless star. Solar radiation heats our atmosphere and drives our climate. The solar wind shapes our magnetosphere and modulates the influx of cosmic rays. Geomagnetically induced currents flow through our crust just as they flow through our power lines. We are part of a grander system where the Sun and Earth interact constantly intimately through multiple well-defined physical channels. The ancient intuition that events in the heavens subtly influence events on Earth may contain more profound truth than modern science initially credited, not through mystical forces or astrological influences, but through measurable physical mechanisms that we are only beginning to truly understand and quantify. For earthquake prediction, the implications are potentially significant. If solar activity modulates earthquake timing even slightly, then continuously monitoring space weather could provide an invaluable additional tool for assessing seismic risk. Not a crystal ball that precisely predicts exactly when and where an earthquake will strike, but a factor that subtly elevates or reduces probability on timescales of days. Combined with other sophisticated monitoring methods such as strain measurements, GPS deformation tracking, and seismic pattern analysis, solar activity data might improve our ability to issue more meaningful warnings. Current earthquake prediction remains notoriously unreliable. Despite decades of intensive research, no method has proven capable of predicting specific earthquakes with useful accuracy and lead time. The best we can currently do is identify regions at elevated long-term risk and issue general warnings when unusual patterns appear. Any additional genuinely accurate information that improves forecasting would be immeasurably valuable. Research into the Sun-earthquake connection continues globally. The Chinese-Italian CSES Limadu mission, launched in 2018, carries instruments specifically designed to study possible influences of solar activity and ionospheric modifications on seismicity. A follow-up satellite is already planned. Ground-based networks monitor electromagnetic anomalies that some researchers believe may precede major earthquakes. Theoretical work strives to identify and refine the physical mechanisms that could truly link solar variability to crustal stress release. The scientific jury, however, remains out. Mainstream seismology continues to view the solar connection with considerable skepticism, pointing to the many failed claims of earthquake prediction methods over the decades. Extraordinary claims, after all, require extraordinary evidence, and the evidence so far, while profoundly intriguing, has not yet reached the threshold that would compel widespread scientific consensus. But science advances by fearlessly investigating anomalies, by taking seriously those observations that do not neatly fit existing paradigms. If there is a genuine connection between solar activity and earthquakes, ignoring it serves no one. The recurrent correlation found in multiple independent studies demands a robust explanation. Either the statistics are flawed, or there is a real physical phenomenon that our current models of earthquake physics do not yet incorporate. As coronal holes continue to open on the Sun, as high-speed solar wind streams continue to wash over our planet, seismologists will continue to vigilantly monitor the ground beneath our feet. Perhaps one day the connection will be fully understood and seamlessly incorporated into earthquake hazard assessments, offering humanity a new layer of preparedness. Or perhaps future research will definitively rule out any significant link. For now, we watch both the Sun above and the Earth below, acutely aware that we still have much to learn about how our star and our planet dance together through the boundless expanse of space. Chapter 8: Humanity's Reach. touching the Sun with Parker Solar Probe. On Christmas Eve 2024, humanity achieved something that would have been deemed utterly impossible. By previous generations, a spacecraft flew directly through the atmosphere of a star. NASA's Parker Solar Probe, launched with immense anticipation, in August 2018 completed its closest ever approach to the Sun, passing a mere 3.8 million miles from the solar surface. To put this incredible feat into perspective, Mercury, the innermost planet in our solar system, never gets closer than 29 million miles from the Sun. Parker ventured nearly 8 times closer, bravely plunging into the corona itself, that mysterious superheated outer atmosphere where temperatures inexplicably soar to millions of degrees. At its closest approach, the spacecraft was travelling at approximately 430,000 miles per hour, making it faster than any human-made object in history. At this mind-boggling velocity, you could travel from New York to Los Angeles in under 20 seconds. Parker was moving so rapidly that the Sun's immense gravity could not permanently capture it. The probe was instead on a meticulously calculated trajectory that would swing it back out into the inner solar system before it returned for yet another daring close pass. The mission is fittingly named for Eugene Parker, the visionary physicist who first predicted the existence of the solar wind in 1958. When NASA announced the naming in 2017, it marked a historic first. The agency had never before named a spacecraft after a living person. Parker, then 91 years old, attended the launch in Florida the following year, a testament to his profound legacy. He passed away in March 2022 at the age of 94, having lived to see the first groundbreaking results from the mission that proudly bore his name. The engineering challenges of constructing a spacecraft that could not only survive but also operate flawlessly within the Sun's scorching corona were immense, pushing the boundaries of human ingenuity. At 3.8 million miles from the solar surface, the Sun appears nearly 20 times larger than it does from Earth. The solar intensity at that distance is roughly 500 times greater. The sunward side of the spacecraft experiences temperatures approaching an infernal 1,800 degrees Fahrenheit. The ingenious solution was a revolutionary heat shield called the Thermal Protection System (TPS). This carbon composite shield measures about 8 feet in diameter and 4.5 inches thick. Despite facing such extreme temperatures, the shield remarkably keeps the spacecraft body and its delicate instruments at a relatively comfortable 85 degrees Fahrenheit. The core of the shield, a specialized carbon foam, is 97% air, making it surprisingly light while providing unparalleled insulation. Behind this life-saving shield, 4 sophisticated instrument suites diligently gather unprecedented data about the Sun and the solar wind. The field's experiment meticulously measures electric and magnetic fields, radio emissions and shock waves within the turbulent solar plasma. The Integrated Science Investigation of the Sun, as IS, pronounced ESIS studies, energetic particles accelerated by intense solar activity. The solar wind electrons, alphas and protons, sweep instrument directly samples the solar wind plasma, while the wide-field imager for Solar Probe WISP-R captures visible light images of the corona and intricate solar wind structures. Parker has already profoundly transformed our understanding of the Sun. Among its most significant discoveries are structures termed switchbacks, dramatic sudden reversals of the magnetic field that occur abundantly in the near-Sun solar wind. These unexpected zigzag patterns where the magnetic field abruptly flips direction before flipping back were completely unanticipated. They may hold crucial keys to understanding how the corona is heated to such extreme temperatures and how the solar wind is accelerated to its tremendous velocities. During its record-breaking December 2024 close approach, Parker flew directly through the corona during a period of significant solar activity. Its WISP-R camera captured stunning, unprecedented images of coronal mass ejections erupting from the Sun. In these incredible images published in late 2025, scientists observed something truly remarkable. Not all the material in a CME actually escapes the Sun's gravity. Some of it unexpectedly falls back. These inflows, as researchers have termed them, show elongated blobs of solar material raining back toward the solar surface after a CME passes. This fascinating phenomenon had been glimpsed from a distance by other missions like SOHO and Stereo, but Parker's extreme close-up view revealed intricate details never before seen. The inflows appear to be magnetic field lines that stretched outward during the eruption, but then powerfully snapped back carrying trapped plasma, with them a cosmic elastic band. This discovery has significant implications for our understanding of space weather. If some CME material regularly falls back to the Sun, rather than escaping it, fundamentally affects the total amount of magnetic flux and plasma that actually propagates through interplanetary space. It also means that CMEs dynamically reshape the solar corona in subtle but significant ways, potentially influencing the trajectory and intensity of subsequent eruptions. Parker has also made critical inroads into investigating the long-standing mystery of the corona's anomalous heating. Why is the outer atmosphere of the Sun hundreds of times hotter than the surface below it? This profound question has puzzled physicists for over 80 years. Parker's direct observations point strongly toward magnetic reconnection and wave heating as key mechanisms. The switchbacks it detected may represent magnetic field lines actively reconnecting and releasing energy into the surrounding plasma. Alphin waves, oscillations that propagate along magnetic field lines, appear to carry significant energy outward from the Sun and may deposit that energy into the corona through various damping processes. The mission has completed multiple daring passes through the corona since first entering it in April 2021. Each approach adds invaluable data to the set and refines our understanding by sampling the diverse conditions that give rise to different types of solar wind flying through coronal holes, active regions, and the intricate boundaries between them. During one particular encounter, Parker discovered a surprisingly quiet zone within what was expected to be turbulent corona. A sharp-eyed graduate student analysing the data found regions where the magnetic field and plasma remained remarkably stable, even in such close proximity to the Sun. These calm patches within the cosmic storm raised new, intriguing questions about the complex structure and dynamics of the inner corona. The spacecraft's incredible journey to such close solar approaches required an innovative and audacious orbital strategy. Parker utilizes Venus gravity assist to gradually shrink its orbit, drawing it ever closer to its fiery target. Over the course of the mission, it has flown by Venus 7 times each encounter, precisely bending its trajectory and progressively dropping its closest approach distance to the Sun. The final Venus gravity assist occurred in November 2024, meticulously setting up the record-breaking December flyby. The orbit Parker now follows has a period of approximately 88 days. Every 88 days, it swings from a distant aphelion of about 0.73 astronomical units, roughly the orbit of Venus, down to its perilous closest approach of 0.04 astronomical units, deep within the corona, then back out again. The spacecraft will continue making these close passes with additional approaches at the same incredible distance occurring in March and June 2025. Parker's primary mission technically concluded in June 2025 with its 24th orbit of the Sun. However, the spacecraft remains healthy and continues to diligently collect data. NASA is actively reviewing options for an extended mission that could continue operations for years to come, potentially gathering invaluable observations across an even greater portion of the solar cycle. The data returned by the Parker Solar Probe is not merely of academic interest. Understanding the Sun's innermost atmosphere and the precise origins of the solar wind directly and dramatically improves our ability to forecast space weather. Every CME that erupts, every high-speed stream that flows from a coronal hole, begins its arduous journey in the very regions Parker is now directly sampling. By understanding the intricate physics at the source, we can far better predict what will ultimately arrive at Earth days later. Future missions will undoubtedly build upon Parker's extraordinary achievements. The European Space Agency's Solar Orbiter, launched in 2020, carries a suite of remote sensing instruments that perfectly complement Parker's in-situ measurements. At times, the two spacecraft have precisely coordinated observations providing multiple viewpoints of the same dynamic solar structures, a true multi-dimensional perspective. This heliospheric Great Observatory approach, combining data from many spacecraft at different locations, represents the exciting future of solar research. Plans are actively developing for even more ambitious missions. Concepts have been proposed for spacecraft that would impossibly with current technology, but potentially achievable with advanced solar sails hover in place directly above the Sun's poles. Such a visionary mission could continuously monitor the polar regions where large coronal holes typically form during solar minimum, providing crucial early warning of high-speed streams long before they rotate toward Earth. For now, the Parker Solar Probe continues its lonely heroic dance around the Sun, the fastest and among the most heat-resistant objects humanity has ever conceived and created. Each daring close pass brings new data, new discoveries, new profound insights into the star that gives us life. Eugene Parker lived to see his theoretical prediction confirmed by direct tangible observation. The solar wind is real. Its precise origins in the corona are now being measured for the very first time. The spacecraft bearing his name has in essence touched the Sun. As Noor Rawafi, the mission's project scientist, eloquently stated upon confirming Parker's survival of its December 2024 flyby, "We are seeing atoms and molecules in the solar atmosphere colliding with our spacecraft. We are there. We have embraced a star." Chapter 9, The Cosmos's Canvas Auroras Unveiled, stand on a dark night in the high latitudes far removed from the polluting glow of city lights, when the Sun has been particularly active and the sky is clear, unblemished. If fortune favours you, you will witness one of the most spectacularly beautiful and profound natural phenomena our planet graciously offers. It begins as a faint glow easily mistaken for distant city lights on the horizon, or the first tentative hints of dawn. But this glow is unmistakably green, not the orange or white of civilization. It strengthens, it moves. And then, if the geomagnetic activity is sufficiently powerful, ethereal curtains of light unfurl across the vast expanse of the sky, rippling and dancing in patterns that seem almost alive, imbued with a cosmic sentience. This is the Aurora Borealis, the Northern Lights. The exact same breathtaking phenomenon occurs in the southern hemisphere, known as Aurora Australis, the Southern Lights. Together they are simply the polar lights or Aurora Polaris, visible dancing reminders that Earth exists not in isolation but profoundly within the dynamic influence of an active, ever-changing star. Humans have gazed upon and been captivated by auroras for as long as we have inhabited the high latitudes. The earliest dated record comes from ancient Chinese chronicles describing unusual lights in the sky, around 977 BCE. Norse mythology attributed the lights to the shimmering Bifrost Bridge connecting Earth to Asgard, the realm of the gods, or to reflections from the polished shields and armour of the Valkyries. Inuit traditions speak of spirits playing ball with walrus skulls in the celestial realm. Finnish legends called the phenomenon revontule, meaning fox fires, stemming from a magical story of an Arctic fox sweeping its tail across the snow, throwing sparks into the night sky. The scientific understanding of auroras, however, developed far more slowly, painstakingly over centuries. The term Aurora Borealis was coined by Galileo Galilei in 1619, a poetic fusion of Aurora, the Roman goddess of dawn, with Boreas, the Greek god of the north wind. But it was not until the 20th century that physicists, through meticulous research, began to unravel the true intricate mechanism behind this celestial ballet. Auroras are fundamentally caused by charged particles emanating from the Sun colliding with atoms and molecules in Earth's tenuous upper atmosphere. This basic statement, however, contains layers of complexity that scientists are still actively working to fully comprehend. The process begins, as always, with the Sun. The solar wind, the continuous outflow of protons and electrons, carries these charged particles toward Earth at speeds ranging from 300 to 800 kilometers per second. When this plasma reaches our planet, it encounters the magnetosphere, the expansive region of space dominated by Earth's intrinsic magnetic field. Most of the solar wind flows around the magnetosphere deflected like water around a resilient stone in a fast-moving stream. But some particles crucially find their way in primarily through the process of magnetic reconnection on the dayside magnetopores. When the interplanetary magnetic field MF is oriented southward, solar wind energy and plasma are efficiently transferred into the magnetosphere. This energy then flows along magnetic field lines toward the poles, accumulating in the magnetotail on the night side of Earth. When conditions align perfectly, instabilities within the magnetotail trigger explosive reconnection events aptly called substorms, releasing the stored energy and dramatically accelerating particles toward Earth. These accelerated particles, predominantly electrons but also some protons, spiral down along magnetic field lines into the upper atmosphere at altitude typically between 100 and 300 kilometers. There they violently collide with atmospheric gases, exciting the atoms and molecules to higher energy states. When these excited particles then return to their lower ground state, they release the excess energy as light, the visible photons that paint the sky. The vibrant colours of the aurora depend intimately on which atmospheric gases are excited and at what precise altitude the collisions occur. Green is by far the most common auroral colour, a verdant glow that dominates most displays. It originates from excited oxygen atoms at altitudes between 100 and 300 kilometers. When an energetic electron collides with an oxygen atom, it can excite an electron within that atom to a higher energy level. This particular transition from one excited state back to the ground state releases a photon of distinct green light with a wavelength of approximately 157.7 nanometers. The excited state of this oxygen atom is relatively long-lived, about 3/4 of a second, which means the oxygen atom must avoid further collisions for long enough to emit its characteristic light. At the atmospheric densities found between 100 and 300 kilometers, this is usually possible. Red aurora appears at higher altitudes, typically above 300 kilometers, and sometimes as a subtle lower border beneath the green. The high-altitude red comes from a different oxygen transition that produces light at 630.0 nanometers. This excited state is even longer-lived, requiring nearly 2 full minutes to decay. At very high altitudes, where the atmosphere is incredibly thin, oxygen atoms can indeed wait this long between collisions. The lower red border, when present, typically originates from excited nitrogen molecules. Blue and purple hues are strong indicators of nitrogen involvement. Nitrogen molecules, when struck by high-energy electrons, can become ionized, losing an electron. The ionized nitrogen molecule then emits blue light as it recaptures an electron. Purple and pink colors are the result of a beautiful cosmic mixing, combining the red oxygen emissions with the blue nitrogen emissions. The intricate patterns and dynamic movements of auroras are a direct reflection of the underlying dynamics of the magnetosphere itself. The basic structure is the auroral oval, an elliptical band encircling each magnetic pole at approximately 65 to 70 degrees magnetic latitude during quiet times. Within this oval, auroras are almost always present, though they may be faint and subtle. Crucially, the oval expands equatorward during geomagnetic storms, bringing the lights to significantly lower latitudes, captivating new audiences. Auroral forms range from simple, elegant arcs stretching east to west across the sky to incredibly complex curtains, individual rays, mesmerizing spirals, and dynamic shifting structures that can change their appearance within mere seconds. The most dramatic and unforgettable displays occur during substorms, when energy stored in the magnetotail is suddenly explosively released. The aurora may then fill the entire sky, dancing and flickering with an intensity that often makes even sophisticated cameras struggle to capture the sheer awe of the experience. The apparent movement of auroras has a precise physical cause. The curtains and ribbons directly trace the magnetic field lines along which particles are precipitating into the atmosphere. When these field lines shift, or when the region of particle precipitation moves, the visible aurora moves with it, often at speeds exceeding hundreds of meters per second. Waves and ripples propagating along auroral arcs reflect instabilities in the powerful electric currents flowing through the ionosphere. The phenomenon of auroral sound remains a matter of ongoing scientific investigation and some controversy. Many observers, both historically and in modern times, report hearing distinct sounds accompanying bright auroras described variously as crackling, swishing, or hissing. Scientists initially dismissed these reports, calculating that sound waves generated at auroral altitudes could not possibly reach the ground quickly enough to be heard in sync with visual changes. However, recent research suggests that electrophonic effects, where electromagnetic pulses from the aurora induce vibrations in nearby objects like grass hair or eyeglasses, might explain some of these intriguing reports. The phenomenon, however, remains not fully explained, a lingering mystery. The May 2024 geomagnetic storm produced auroras visible far beyond normal latitudes, a truly global spectacle. This extreme event, triggered by a series of powerful coronal mass ejections, drove the KP index to 9, its absolute maximum value. Aurora was observed from locations as far south as Florida, Texas, and Mexico in North America, and from the Mediterranean region in Europe. Social media platforms were inundated with breathtaking photographs of red and green skies from countless observers who had never witnessed the phenomenon before. For communities at high latitudes, auroras are a regular cherished part of life. In places like Tromsø, Norway, Fairbanks, Alaska, and Yellowknife, Canada, aurora viewing has become a thriving tourist industry. Experienced guides lead groups into dark wilderness areas equipped with specialized cameras and warm clothing, all hoping for clear skies and active, mesmerizing displays. The powerful combination of solar maximum conditions and the long, dark nights of the northern winter makes the current period particularly favorable for aurora tourism. Auroras, it's important to remember, are not unique to Earth. Any planet with a significant magnetic field and an atmosphere can produce them. Jupiter, for instance, displays spectacular auroras at its poles, powered not only by the solar wind but also by particles from its volcanically active moon, Io. Saturn's majestic auroras have been imaged by the Hubble Space Telescope and the Cassini spacecraft. Even Mars, which largely lacks a global magnetic field, exhibits faint localized auroras in specific regions where crustal magnetic fields exist. Scientists meticulously study Earth's auroras using a combination of ground-based cameras, radar systems, and magnetometers, as well as comprehensive satellite observations. The Themis mission, with its network of ground observatories across North America and 5 spacecraft in orbit, specifically investigates substorm dynamics. Citizen science projects like Aurorasaurus actively collect real-time reports from observers worldwide, helping researchers track the true extent and intensity of auroral activity. For those fortunate enough to witness a major auroral display, the experience is often described as profoundly transformative. The sheer scale of the phenomenon filling the sky from horizon to horizon, the ethereal movement that seems almost intentional, and the colours shifting and evolving, all combine to create an overwhelming sense of connection to forces far larger than human concerns. In those moments standing beneath the dancing lights, you're directly watching the sun's breath interact with Earth's magnetic armour. You're seeing charged particles that left the solar surface days ago complete their incredible journey by exciting atoms in the thin upper air, releasing photons that travel the last 100 kilometers to your eyes in less than a millisecond. You are witnessing the universe itself at work, beautiful and indifferent, ancient and immediate. The aurora has danced over Earth for billions of years, ever since our planet first developed a magnetic field and a protective atmosphere. It danced before there were eyes to see it, before life emerged from the seas, before anything on Earth could wonder at its sublime beauty. Now we watch, and we understand, and we are profoundly grateful for the cosmic show. Chapter 10. Navigating the Solar Future, a call for cosmic resilience. The coronal hole that dramatically opened in December 2025 is not an anomaly that will simply close and disappear. If anything, the persistent patterns observed throughout this solar cycle strongly suggest that we may see even more frequent and larger coronal holes in the years ahead as solar cycle 25 inexorably descends toward its minimum around 2030. This is the inherent predictable nature of the solar cycle. Solar activity consistently rises and falls in an approximately 11-year rhythm, but the descending phase is not a mere return to quietude. It brings its own distinct forms of solar influence upon Earth. Coronal holes expand and persist, particularly near the poles, but also critically at lower latitudes where they can directly affect our planet. High-speed solar wind streams become recurring features of space weather, sweeping past Earth every 27 days as the same coronal holes rotate with the Sun like a cosmic lighthouse beam. What can we realistically expect in the years immediately ahead? Through late 2025 and into 2026, solar activity should remain elevated. We may not have reached the absolute true peak of solar cycle 25. Some cycles historically exhibit double maxima, with a second distinct peak of activity following the first by a year or more. Whether this current cycle follows that intriguing pattern remains to be seen, but major flares, powerful coronal mass ejections and intense geomagnetic storms will continue to be a significant possibility throughout this period. By 2027 or 2028, a clearer, more discernible decline in overall solar activity should become apparent. Sunspot numbers will gradually diminish. Active regions will become less frequent and less magnetically complex. But paradoxically, as the magnetic field simplifies, coronal holes will grow larger and more stable. The polar holes that persistently exist through minimum can expand to cover significant fractions of the visible solar disk. Equatorial and transequatorial holes may become more common as magnetic field evolution creates open field regions at lower latitudes directly facing Earth. These expanding coronal holes will continue producing high-speed solar wind streams. While the peak intensity of the most extreme geomagnetic storms tends to correlate with solar maximum and intense CME activity, the recurring disturbances from coronal holes during the descending phase and minimum can still reach moderate to severe storm levels, posing significant risks. Power grid operators, satellite operators, and aviation authorities will need to maintain constant vigilance as these recurring events demand sustained preparedness. By 2029 or 2030, we should approach solar minimum, the quietest phase between cycles. Sunspots may disappear entirely for weeks at a time. Solar flares will become rare. Coronal mass ejections will diminish in both frequency and intensity. But the heliosphere itself will change. With weaker solar magnetic activity, the protective bubble of solar influence surrounding our solar system will subtly shrink. Cosmic rays from beyond the heliosphere will penetrate more easily, slightly increasing radiation levels at aviation altitudes and for astronauts in deep space. Solar cycle 26 will then commence ushering in the next chapter in our star's magnetic evolution. Predictions for cycle 26 are not yet possible with confidence, as the forecasting methods that fail to accurately predict the strength of cycle 25 dramatically demonstrate the limits of our current understanding. Some researchers speculate that we may be entering a period of generally stronger cycles, potentially ending the trend of weakening that characterize cycles 21 to 24. Others remain cautious, noting that solar behavior over century-long timescales is still poorly understood, a vast frontier of knowledge. The longer-term future of solar activity contains even deeper uncertainties and profound questions. Some scientists have proposed that the Sun might be approaching a grand minimum, an extended period of very low activity, similar to the Maunder minimum of 1645 to 1715. During that 70-year period, sunspots nearly disappeared entirely. Whether the Sun can enter such a state again, and what the far-reaching consequences might be for Earth's climate and space environment, remains a topic of intense scientific debate. What is absolutely certain, however, is that the Sun will continue its relentless cycles for billions of years to come. Nuclear fusion in its core will gradually convert hydrogen to helium, slowly increasing the Sun's luminosity over hundreds of millions of years. This increasing brightness will affect Earth's climate in profound existential ways. Eventually, perhaps 1 billion years from now, the sun will become too bright for liquid water to exist on Earth's surface. Life as we know it will face existential challenges long before the sun finally exhausts its hydrogen fuel and expands into a terrifying red giant. These deep future transformations are truly beyond human timescales, almost unimaginable. What matters most for our civilization is the near term, the years and decades during which we must learn to coexist resiliently with a variable dynamic star. Space weather preparedness has indeed improved significantly since the Quebec blackout of 1989, a wake-up call for our technological age. NOAA's Space Weather Prediction Center now issues daily forecasts and critical alerts for geomagnetic storms, solar radiation storms and radio blackouts. A sophisticated fleet of satellites constantly monitors the sun and the solar wind, providing invaluable data for forecasting models. The Deep Space Climate Observatory, DSCO-VR at the L1 Lagrange point, offers a crucial 15 to 60 minutes warning of CME arrivals. New satellites launching in the coming years will add further enhanced monitoring capabilities, but significant gaps in our preparedness still remain. Warning time for the most extreme, potentially catastrophic events is measured in minutes to hours, not days, which is often insufficient for comprehensive protective actions. The ability to predict exactly which CMEs will be geo-effective and how strong the resulting storms will be remains frustratingly limited. Many power grid operators still lack real-time monitoring of geomagnetically induced currents in their systems, a critical blind spot. Standards for space weather resilience vary widely between countries and even between industries, creating a patchwork of vulnerability. The European Space Agency ESA is actively developing the Vigil mission planned for launch around 2031. This visionary spacecraft will be positioned at the L5 Lagrange point, trailing Earth in its orbit around the Sun. From this unique vantage point, it will observe the Sun from the side, effectively detecting active regions and CMEs before they rotate to face Earth. This could extend crucial warning times, significantly providing days of advance notice for some events, a game changer for preparedness. Research continues relentlessly on improved forecasting models. Machine learning techniques are being applied to the wealth of solar data accumulated over decades, seeking hidden patterns. Magnetohydrodynamic MHD simulations model the propagation of CMEs through interplanetary space with increasing realism and accuracy. Coupled models connect solar observations to magnetospheric response to ground-level effects, aiming for a holistic understanding. The ultimate goal is forecasting that rivals terrestrial weather prediction in both accuracy and lead time, giving humanity the foresight it desperately needs. Meanwhile, efforts to harden critical infrastructure proceed unevenly, often hampered by economic considerations and competing priorities. Some utilities have indeed installed GIC blocking devices on their most vulnerable transformers. Some satellite operators have developed meticulous procedures for safe mode operations during extreme events. Some governments have commissioned detailed studies on national resilience to space weather, but progress is in many ways slower than the science would suggest is prudent and necessary. The next Carrington-class event will come. Whether in 10 years or 100 years, the sun will eventually produce a storm of that devastating magnitude. And if it is directed toward Earth, our fragile technological civilization will face a test unlike any it has ever experienced. The Quebec blackout affected one province for 9 hours. A Carrington event could affect continents for months or even years, fundamentally resetting our interconnected world. Preparing for such an event is not alarmist. It is rational, strategic risk management, a testament to human foresight. We prepare for earthquakes, hurricanes, and pandemics with earnestness. We should prepare equally for the certainty that the sun will occasionally remind us of its overwhelming power. For those of us watching the sun in 2025, the immediate future offers both profound challenges and invaluable opportunities. The giant coronal holes appearing during the solar maximum are vivid previews of what the descending phase may bring in amplified form. Each high-speed stream that washes over Earth teaches us something new and vital about the Sun-Earth connection. Each geomagnetic storm tests our monitoring systems and refines our response procedures. And each aurora that dances across the sky, visible from latitudes that rarely witness such displays, reminds us of the profound, inextricable connection between the nuclear fire burning 93 million miles away and the thin envelope of atmosphere and magnetic field that makes life possible on our small blue world. The sun has burned for 4.5 billion years. It will burn for 4 billion more before swelling into a red giant and eventually shedding its outer layers. Compared to these cosmic timescales, human civilization is but a brief flicker in the vastness of eternity. Yet in our brief moment, we have developed the extraordinary ability to understand our star, to monitor its dynamic activity, and to begin, however imperfectly, protecting ourselves from its inherent hazards. The dark wound on our star, the coronal hole staring at us from December's sun, is simultaneously both a threat and a profound teacher. It threatens our satellites, our power grids, our communication systems, the very infrastructure of modernity. But it also teaches us invaluable lessons about magnetic fields, plasma physics, and the fundamental processes that govern stars throughout the universe, connecting us to the grand cosmic drama. We are and forever will be students of a restless star. The classroom is dangerous but undeniably magnificent. And the lessons, if we pay diligent attention, might just help us survive the next great storm. The wound remains open. The solar wind continues to blow an invisible river of power, and we continue to watch, to learn, and to prepare for whatever our stormy star sends our way, knowing that curiosity and knowledge are our greatest shields against the unknown.